Hello everyone, welcome to this video. This time we're going to be solving Griffiths problem 2.7 as it appears on his book, Introduction to Quantum Mechanics, 3rd edition. Now I did make some slight adjustments so that it fits better what we have seen here on this course, but it is basically the same thing. So in this problem we are told that there's a particle in the harmonic oscillator potential that has the initial wave function, which is a combination of psi0 plus psi1. And the first thing we want to do is normalize this function so that we can find the constant a. So let's go ahead and do that here. So part A, we need to normalize. So that means that we have to do the integral 1 is equal to the integral from minus infinity to infinity of our wave function, right? Which is going to be this big psi x comma 0 and the modulus of this squared dx. For the modulus, as we have done many times before, this is just going to be the conjugate of the wave function times the actual wave function. So this is going to be a squared psi0 conjugate plus psi1 conjugate. I'm just going to drop the a of x for now because there's no other variable, so it's not that important to specify, times psi0 times psi1 dx. So now we just multiply this through, we get 1 is equal to the integral minus infinity to infinity of a squared times, and then we get psi0 conjugate psi0 plus psi0 conjugate psi1 plus psi1 conjugate psi0 plus psi1 conjugate psi1 and all of this dx. But here, as we have seen in previous videos, we have to remember these wave functions are orthogonal, so this is 0, and well, they are also not orthonormal, in fact, so these ones are 1, right? So there's no need to actually write the write in the wave function. So there's you could do that, but you get to the same result, and it would be much more tedious. So now when we integrate this, we get that a squared times 1 plus 1, right? 1 comes from this first part, 1 comes from this, right? Because when we integrate it, we get 1, they are normalized. So now we just here solve for a squared, which is going to be 1 divided by 2. And so a is going to be 1 divided by the square root of 2. Okay, so our wave function psi of x comma 0 is going to be 1 divided by square root of 2 times psi0 plus psi1. Okay, so this is the first part. You could obviously here put in the actual wave functions psi0 and psi1, and that's actually something we will do when we start doing part B, right? So in part B, we are asked to find this wave function as a function of time, right? We have to incorporate the time dependence, and then we have to find the probability density. So in order to do that, remember, usually this psi of x comma t was some linear combination of our psi n's, right? But in this case, our wave function only has 2 states, so this summation is just going to go from this 0 to 1, in fact, because it's only the 0 and 1 state. And well, the cn's happen to be the same. They're both 1 divided by square root of 2. So this is already in this form, right? And then there was this e to the minus I e t divided by h bar. So all that we are actually missing is to multiply en, each psi, by this exponential with its energy. So let's remember that the energy of the nth state is just 1/2 plus n h bar omega. So the energy of the first state is going to be, well, let's begin with the ground state. So that's just going to be h bar omega divided by 2. And the energy of the first state is going to be 3 h bar omega divided by 2. Okay, so there's that. Now we can just put all of this into our psi right here. Psi of x comma t, right? Now we are incorporating this time dependence. It's going to be 1 divided by the square root of psi0 e to the minus I, and now comes this energy, and the h bar here will cancel out the h bar in the denominator, so we get minus I omega t divided by 2, And in the second one, we have plus psi 0 e to the minus I. So there's a 3 now. So minus 3i. The h bar here will cancel out the one in the denominator, minus omega t. Okay, we can here actually factor out this e to the minus I omega t. So we get, oh, this is divided by 2, by the way. This is e to the minus I omega t divided by 2. So we get psi 0 plus psi, whoops, I'm sorry about that. This is psi 1, slight typo, plus psi 1 e to the minus I omega t. Okay, so this is this psi of x comma t. And we still can and will have to replace and write in here the expressions for psi 0 and psi 1 in order for it to be like actually a complete solution. So let us quickly go ahead and do that. 1 divided by square root of 2. Now we have found this in previous videos. I will write them down here just so that you can remember. This is pi h bar to the 1/4 power e to the minus psi squared divided by 2. And psi 1 is m omega pi h bar to the 1/4 power times, I think it was 2 divided by the square root of 2 times psi e to the minus psi squared divided by 2. Okay, so with this in mind, we can now put this into our wave function, and we can see that we can factor out this right here because it's both here, I mean in the psi 0 and in this psi 1. So we can write this much better. So I meant to erase this line here, which I wrote down much early. So now we have, okay, it was actually fine. M omega pi h bar, the 1/4 power, times e to the minus psi squared divided by 2, e to the minus I omega t divided by 2. Well, psi 0, now this is just going to be 1, plus, and here we are going to be left with 2 divided by the square root of 2 psi e to the minus I omega t. Now there is something we can do here because we can rationalize this expression. It's not really that important, but we can do that. And we can just multiply in the numerator and denominator by the square root of 2, so that we get 2 square root of 2 divided by 2, and the 2 cancels out. So that's going to be the same as just square root of. So it looks a little bit cleaner. Okay. And I'm actually also going to erase these because we already used them. We don't really need it to keep it around. Okay. So this is the final result we wanted for this part. And now we want to apply it to find the probability density. Remember, the probability density is going to be this psi of x comma t in its absolute value squared. So let's now calculate that. And just as a quick reminder, this is psi, I don't know why I wrote down that line. Okay. Psi conjugate psi, right? So let's do that. So when we multiply this, we got this, all these constants are here. So let's begin with that. These things are real, at least this 3 first terms. So we're just going to get the squared of them. So 1 divided by 2 m omega pi h bar to the 1/2 power e to the minus psi squared. And then we get this e to the minus I omega t divided by 2. But when we multiply it by its conjugate, we're going to get e to the plus I omega t divided by 2 minus I omega t divided by 2. So we get just 0 in the exponent. So this is just going to be 1. So we don't really need to write it down. So all that is important is going to be what is in this parentheses. So let's first write down the conjugated version. So we get 1 plus square root of 2 psi e to the plus I omega t. And then we have to multiply by the regular version, which is just 1 plus square root of 2 psi e to the minus I omega t. And well, now we go ahead and multiply this parentheses. So I think the square term, yeah. this 2 right there did not come. Okay, so when we multiply the first part, just 1 times 1, 1, no big deal there. Then we get, let's see, 1 times this square root of 2 psi blah blah blah, but we also will have this other term. Well, actually, let's not go ahead of myself just in case someone is not quite clear with this. So when we multiply 1 times this right here, we get square root of 2 psi e to the minus I omega t. Then we multiply the square root of 2 psi e to the plus I omega t times 1, and we get square root of 2 psi e to the I omega t. And then we finally multiply these two together. The exponents will cancel out, and we get plus 2 psi squared. So here we can actually do something that is very important, and it's important that if it doesn't happen now, don't worry about it. In your courses in quantum mechanics and just in the future, there should be some sort of sense tingling, and if it isn't, then you have to start training it when something like this happens. Okay, so let me just write down all of these things. So let's go to 1 plus, I'm going to write this here, psi squared. Now let's factor out the square root of 2 times psi, square root of 2 times psi, and we get e to the I omega t plus e to the minus I omega t. Now, whenever you see something like this, I really hope you think, oh, that seems cosine or sine. Like if you can't really tell which one it is, it's okay for now, but this should look like a sine or a cosine. In this case, it's going to be a cosine, but whenever you have the e to the I something plus or minus e to the minus I and that same something, that is something you can write as a cosine or a sine, right? Because cosine of, let's say, well, I don't know, theta, this is going to be e to the I theta plus e to the minus I theta divided by 2, and sine of theta, this is e to the I theta minus e to the minus I theta divided by 2i, right? This just comes, I think we talked about this in a previous video, so and you can just look for the derivation. It's really quick, just from Euler's formula, right? But this cosine is exactly what we have here, but we are missing that divided by 2. So this is actually twice the cosine of omega t, because in this case, theta is just omega t. So let me just copy this. I do not feel like writing it down again. So, okay. So here, let's just, instead of all of this, we can just write 2 times cosine of omega t. Right, and we can see that in this case, unlike in previous cases, this probability density does depend on time, right? Because it's oscillating. Because this is the quantum harmonic oscillator, so it is kind of important that it actually oscillates. And I'm just realizing I'm missing a parenthesis. It's not really that much of a big deal, but whatever. Okay, so this is what we were looking for, this psi squared, right? The probability density. That was part B. There's not really much more we can simplify here. We could put that 2 in there, but it doesn't really change much. So part C asks us to find the expectation value of x as a function of time, and then to determine what is the amplitude and frequency of the oscillation. So let me go back, take this result and take it with me. So there we go. Because what we want to do now is just find this expectation value of x, which, remember, is going to be the integral of psi squared x dx. Okay, but we are working with psi here, so let's just write, because remember, psi is square root of m omega divided by h bar times x. So dx is, well, let's begin with x. Actually, x is going to be h bar m. We've done this many times before, so I hope that there's not much confusion. And dx is going to be, well, the same, but in this differential form. Okay, so let's put this into the equation here for the expectation value. We get integral from minus infinity to infinity of, now we get these constants here, which are going to turn into h bar m omega. And now comes this entire thing there. So we get all of this. Oh, I'm kind of running out of space here, but well, I guess I could write this a little closer, but well. And now we have to multiply this by psi, which I will just write over here. And well, obviously this is d psi, so whatever, just d psi, right? So let's put all of the constants outside. We'll see that they will kind of cancel out because there's an h bar to the first power times this whole thing to the 1/2 power. So we get h bar m omega. Oh, yeah, because yeah. H bar, let me just double check. M omega, yeah, and there's going to be a pi here. So it's the square root of all of this. And then we got this 1/2, and I think that's all of the constants. Yes. And then we got the integral. So let's take a look at the integral now, because when we multiply this psi, and let me do it right here, this psi right here, let's multiply it into the bracket. So this first one is just going to be psi. Oh, this is squared, by the way. When I copied it, it must have lost the squared. This is going to be 2 psi cubed, and this is going to be psi squared. Now, I hope that this rings a bell, because this is an odd function, right? Odd function even in an even, no, not even, sorry, in a symmetric interval, this is just going to be 0. Right? Same with this right here. You don't have to integrate this. If you know that it's even symmetric interval, it's going to be 0. So the only thing that actually does something is this right here. So let us now write it down here. So we get 2 square root of 2 psi squared cosine of omega t e to the minus psi squared d psi. Okay, so this is the integral that we now have to solve. Okay, I think I'm going to copy some things that are not supposed to come along, but whatever. So there's this 0 and this infinity. So this is to infinity. Okay, so now we can just pull more of these constant outside. This 2 will cancel out this. So we get square root of 2 h bar divided by pi m omega. And now we get the, well, and the cosine can also go outside because it does not depend on psi. So we are left with the integral from minus infinity to infinity of psi squared e to the minus psi squared d psi. Now we have solved this integral many times before. If you are unsure, just go back and watch some of the other videos on the quantum harmonic oscillator. In fact, the one of the expectation values, I think, is where we did the most of these integrals. So you can go and look at there. Because this was just the square root of pi divided by 2. So we do that, we get square root of 2 h bar pi m omega cosine of omega t times square root of pi divided by 2. So this pi's would cancel out, and we are going to be left with h bar 2m omega square root cosine of omega t. So what we can see here, this is going to be then the expectation value of x. We can see that it has an amplitude of oscillation of h bar divided by 2m omega, and it has an angular frequency, well, of just omega, right? So this is then the solution to this part of the problem. Okay, so as before, there wasn't too much new here. It was just integrating and, well, noticing that these exponentials were just going to be the cosine. Now we want to use the result of C, which I will put back on the screen, this right here, to determine the expectation value of the momentum, because you could go ahead and use, you know, the definition, use the sandwich of the wave functions with the momentum operator, but that would be annoying. We want to use something that we discussed previously, which is that this expectation value of the momentum can be written down as the expectation value of mv, because we are talking about classical particles. It's not relativistic, so we can use this normal momentum. So it's going to be m, and this velocity, it doesn't really make much sense to talk about velocity of a particle that doesn't really have a definite position. So we talk about the time change of the expectation value of the position. And that is what we just found. So this is just going to be m times square root of h bar divided by 2m omega times the time derivative of the cosine, which is just going to be minus this whole thing, sine of omega t times omega. So, well, now we can do a few cancellations here in the square root. We are going to be left with m h bar omega divided by 2 times the sine of omega t. Right, so that is going to be our result for this part, and that is going to be this problem. In the book they put a few more things, like checking the Ehrenfest theorem, but we have not talked about it, so I decided to skip it for now, unless at some point I want to include the Ehrenfest theorem. But for now, this is the result. As you can see, there's really not much new. Once you know what the wave functions are, you can calculate everything quite easily. So that is why the main problem here usually is to find the set wave functions, which is also why we dedicated those videos to explaining how we did it and just how to do it in general. Okay, so that's going to be it. We can now finally be done with the harmonic oscillator. If there's some questions and you would like maybe some more content, let me know and I might add some more videos on it. There's some topics that I maybe didn't discuss. And if not, we are now ready to begin talking about the free particle. So I'll see you then.